clustering, classification, and some methods of each. So, what is the difference between clustering and classification? If we are not familiar with the details, then sometimes it is easy to mistake classification or clustering as one another. So, what is classification? Classification is a process of grouping observations or items into something of a class which we already know. And if we know a class and we are trying to group things into those classes, then that is called classification. Groups are well defined. Groups, or let's say classes, are well defined. On the other hand, when we talk about clustering, then we do not care about the classes. No, what is the already existing class? We do not care about that. We are going to group the observations based on the similarities among themselves. Similarity and dissimilarity among themselves. So, since we need to know the group name or the class for doing classification, they are often called supervised techniques because we need to know their label. Why? Whereas in clustering, we don't need to know their label why, so we call them as unsupervised. Okay, so now let's start with classification. I will not be talking too much about the theory. You can go ahead and look at the PPTs if you want to know what are the advantages and the disadvantages of different methods of doing classification or clustering. We'll just look at the core concept and maybe try to code some things in Python Jupyter Lab notebook like last time in the end. Okay, so first method for classification that we are going to discuss is linear discriminant analysis, LDA. So the good thing about LDA is that it the core concept or the methodology behind LDA is similar to PCA that we did last week, that is principal component analysis. So if we know PCA, somehow the methodology is not that much different. The end goal is different. So in PCA, what we try to do, we try to in PCA, if you recall, what we try to do is we wanted to shift or rotate or transform our observations into an axis that retains most of the variability of the data. When we say variability, we actually wanted to preserve the information. Preserve information. So when we transform this observations to such an axis, what we wanted to do was we could forego of some of the features or the new axes which were not giving much information, not having much variability. So we were doing that forego of axis not giving much information. In PCA, that is what we were doing. The main concept was align along the axis having greater variability. right? So we are doing that. But in case of this linear discriminant analysis, what we are going to do is we are going to align our observations. So again, we are going to do some transformations here, but the transformations will need the y label of the data. So transformations will need y label, and we are going to transform the data, observation data, that is x, in such a way that we have maximum distance between the mean of different y's, and we have minimum variability, often referred to as here variance, within each group. So these two things, we want to do these two things that are going to govern how we are going to transform our data. So let me try to give you an example through a schematic diagram. So we have here, let's say x1 and x2, and let's say we have some points. I don't have them. Okay, here, some red points and some blue points. So we have labels, right? I am giving them labels when I am giving them two different colors. So since we have only one participant, if you want to answer my question, you can answer by raising hand. If you like, if you are trying to answer the question, you can raise your hand. So I will wait. If you are having uncomfortability in giving the answer, then maybe after a while I will answer this. If other people want to answer, they can pause the video and we can answer the question. The question number one is, I'm going to draw some lines. So I'm transforming this. This is one. Okay, let me give it a different color. This is one axis. This is one axis. And so which axis should I choose for PCA? So if I were to give you this example, then which axis will you choose for PCA? What is the aim of PCA? It doesn't care about the labels. So just forget that there is a red color and blue color. And tell me which axis is going to give you maximum variability. Okay, so I didn't make the 1 and 2, right? So let me give here A and B. This is A, this is B. So which axis is it, A or B? Okay, so the answer for this will be, I want to keep my B axis as my principal axis, because along this axis I am able, okay, along this axis I am able to see that the variability in my data, the information is stored. Whereas along this axis, the A axis, see, there is not much variability. The answer will be A here. Okay. Now, when we talk about our LDA, linear discriminant analysis. Now we want to classify these two groups of data into, just a second, just a second. Yeah. Okay. Oh, so I think there was a problem with Mr. Gulshan who joined. So I will allow you guys to open the microphone, but I request if you have any doubt, then only you switch on the microphone. Okay. So in case of, as I was saying, in case of linear discriminant analysis, I want to classify these two, and I want these data to be aligned in an axis where I can see maximum difference in the mean of red and blue, and all at the same time minimum difference between themselves in that region itself. So my second question is, now you tell me which axis should I project my data for performing LDA? Is it either A or B? Okay, so those of you who said A, it is wrong, because if you take the projections on A, so it will all be, reds will be going here and blue will also be coming here. So it will not be able to do any classification. Whereas if you take the projection on B, then you will have reds along this line and blue along this line, and you can do classification easily. So for this also the answer is B. So if you are trying to uh, use the logic that now B has already been chosen, so B cannot be correct again, so that is a bad idea. Okay, so this is what is the basics, or very basic, behind the LDA. Now in class, the procedure that sir has shown to do this kind of transformation was a bit complicated, and I personally, when I learned this, not not very long time back, so at that time I used a very simplistic approach, which you can use for coding also. If you don't have any if you don't know how to use the packages, then you can use these steps that I'm going to tell you to make your own code to perform this linear discriminant analysis. So we'll take a simple example. Let's say you have two features, x1 and x2, and you have their corresponding label y. So you have some values here, let's say 10, 20, 30, and 15, and x2 you have 5, 4, 1, 7. And let's say that you have their labels. And for simplicity, let me just give here label 1, integer labels, and 2. Now I want to, they may be already separate if you plot it. I'm just giving some rough plot, so I don't have the idea about where their position or the scatter plot, how it will look like. This I'm just giving so that it is easier for me to explain. So now I'll use this label information that I have to perform the LDA. For LDA, let's say I want only one axis, right? So that axis will be named, let's name that as LD1. You can get another axis also. In this particular case, you can get two axes, but let's say I want to choose only one. So let's call that LD1. And the entries in this axis will be given by S, that is W inverse into B. Now what is W? W is pooled within group covariance matrix, and B is intra-group covariance matrix. Now we will see how we actually calculate this W and B. Okay, so to calculate W, this is to calculate W. First, we have to calculate covariance matrix for class or group 1. So, does anyone want to say or want to tell me what will what is the formula for the covariance matrix when we have two variables? Okay, so the covariance for class 1, let me just write it as co1. Okay, at least let's give this a shot. Tell me what will be the dimension of this matrix when you have two variables, two features, and these are examples, number of samples. Then in that case, what do you think is going to be the size of the covariance matrix? If you are not able to tell, no problem. You can go back to the old videos and or the presentations and confirm from there. So the answer is 2 by 2. And what are the entries? Entries will be covariance of x1 with x1, covariance of x2 with x2, covariance of x1 with x2, and covariance of x1 with x2. It is a symmetric matrix. Now the formula of covariance, that I'm not going to tell you. Just remember, just you can go back to the slides and you can refer to this formula. We are just going to go over the overall concept of this thing. So you get the covariance of 1, and then step 2, get the covariance of 2. Okay, so when I said covariance of group 1, then to calculate that you have to only use these values. And when I'm saying covariance of group 2, then you have to use only these values for these features to calculate this covariance. So let me just write this so that it is a little bit easier for you to understand. x1, 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 x2, x2, x2. And in case of group 2, we have same matrix, just the values to calculate the covariance will change. Okay, so this is how we calculate the covariance of group 1 and covariance of group 2. Now we calculate W. W is nothing but a weighted average of these two covariance matrices. And what is this weight? The weight is the number of observations for one group minus 1. So in our case we have 2 for group 1 and 2 in the okay in the second row first element will be see if you remember or if you recall the formula for covariance, it doesn't matter if you are writing So what is the formula for covariance? In the numerator, we write something along the line like this. So if we have x1, x2 covariance, then in denominator something is there, x2 minus. So if you are just writing x2, x1, it will just change. This will change here. The result will not be affected, right? So it doesn't matter if we write x1, x2 or x2, x1. Is that clear? Oh, so it was from Gulshan. Is that clear, Mr. Gulshan? Sorry, I don't know. Yeah, okay. I don't know if you are a boy or girl. So, okay. So now W will look like this. N of group 1 minus 1 into covariance of 1 plus N of group 2 minus 1 into covariance of 2 divided by N1 minus 1 plus N2 minus 1. So this is going to be our W. That is the pooled covariance, pooled within group covariance. And we have to calculate the inverse of this also, so that we can do easily using any operator, or if you want to do using Gauss Seidel, then that also is good. Now, how do we calculate B? B was intra-group variability or covariance matrix, right? So the easy way, a nice way to calculate B is T minus W, where W is the same W that we calculated above, and T is the total covariance matrix. So how do we calculate T? See, remember, when we calculated the covariance matrix for group 1 and group 2 separately, we used only their own group members or observations. But now when I am saying to calculate the total covariance matrix, in this case we are going to use all the values of the feature x2 and all the values of the feature x1. Right? So I don't want to write the matrix again. It is covariance matrix with all the values of features. Okay, so now we try to guess what is the size of this matrix. Yes, anyone want to take a gamble at this? If you're thinking it's too complicated question, then it's not. Let me clarify that. It's simple. So the size of this covariance matrix T is also 2 cross 2 because we have only two features. So when you have T and W, then you can get B is equal to T minus W. And now we have, this was 4, so 5. Now we have, we can easily get the S. It is W inverse into B. So this matrix again will be a 2 by 2 matrix. So step 6 will be to calculate the eigenvalue of, eigenvectors of this matrix. Okay, so how many eigenvectors will a 2 by 2 square matrix will have? It will have two eigenvalues and it will have two eigenvectors. Let's say I put them in one column each. Okay. Now you can again do that by, you can take the eigenvalue with the maximum eigenvector with the maximum eigenvalue and use that to transform your data. So let's say we have v1 as an eigenvector we have chosen because it had the maximum eigenvalue. It will be a 2 cross 1, means it will be having an entry of A and B in a column. Now we use that to transform our data. So we had x1 and x2 in columns. So this, let's say we had n features, so it is n cross 2, and we multiply this with transpose of vector, oh yeah, no, or with the eigenvector that we have chosen, and we get our transform data, that is the LD1 value in this particular column. What will it be? It will be A x1 plus b x2, right? So now when you have this LD1 and you plot these values or you list these values, you will identify that there is a very distinguishable difference between the values that we obtained for the class 1 and that we obtained for the class 2. So in one of the examples, uh, we could see that LD1 for the class 1 was all negative and the LD1 for class 2 was all positive. So if you want to get something like that, then recall that in PCA, before doing all these analysis, what we did was we tried to scale and standardize our data by subtracting by mean. So if you do that in that case, and if you have only two classes, then there is a good chance that you will get LDA distribution around the origin. Okay, so this is about LDA and how do we perform this analysis. Now we will look at a programming example for this later in the session. Okay, so after that we have logistic regression for a classifier. In this logistic regression classification, usually we use this kind of classification for binary classification when we have only two classes. In it is mostly whenever you search for logistic regression examples in YouTube or in any programming sense, then you will find that a lot of times the cancer, malignant or benign, these kind of examples will come because it is used in medical professions to say whether a patient has a certain disease or not based on different temperature readings or blood report. Other a lot of features are there in that. So based on that and their previous encounter with history with other patients, they try to predict whether a patient has a cancer or not, whether it is benign or it is malignant. It can also be used when we have multi-class, that is called multinomial logistic regression, but that is not very common and there are other techniques better than this to do multi-class classification. So mostly it is used for binary classification. Okay. Now to do that binary classification, also this logistic regression, the approach that we follow is a linear approach. It is kind of linear classifier. So the equation, the final equation that we will get in our end product of our classifier will look like this: alpha plus beta x plus error, where x is your feature set, y is your label that you are going to predict, and these alpha and beta are the parameters, with E being the error. We don't need to worry too much about the error. I know there was some things said in class about this error, but they were not used in further subsequent slides for any kind of justification. So we can just ignore this error term for now. So how do we do this kind of classification, logistic regression, if we have for a binary classification? What we do is we try to restrict the outcome y of our logistic regression between 0 and 1. And what we do, we decide a threshold. Usually this threshold is taken as 0.5. So if at all y value is greater than 0.5, we give it as a 1. If y value is less than 0.5, we give it as a 0. So this kind of approach is used when we are training our logistic regression. Right. But in most cases, what you will observe is that y is not limited to 0 and 1, because this is a linear model, right? So if x increases, it can be easily seen that y is going to increase. So it is going to defy the limit that we have already set on it. That is, it has to be above 0 and below 1. If we try to train our model or force our model, then it is going to decrease the value of beta to a much lower value, so that it should never cross um, the upper limit of 1, so, which is not good for our model, because in that case we'll end up predicting always 0, right? So to avoid this problem, sigmoidal function is used. So what is a sigmoidal function? So you would have seen in the slide, in machine learning it is usually given by z is equal to, or a is equal to 1 by 1 plus or minus z. So this is the function which says that if your z is too small, then the value of a is 0, and if z is too big, then the value of a is 1, excluding these points. So it is never actually 0 and 1, but it approaches 0 and 1. And then we decide on the threshold of zero point 0.5, you can do that. So how do we use this sigmoidal function in logistic regression? So let's see how we do this. So we would have seen that instead of y, we are going to call the probability of occurrence, probability of our outcome as p, and we are going to check for p whether p is less than zero point 0.5 or not. So let me just write it here. Probability of outcome or probability of occurrence is much better suited. And then we are going to check for whether p is less than zero point 0.5 or greater than 0.5. And we define a logit function, that is the natural log of the odd ratio of p. So what is an odd ratio? It is p by 1 minus p. So we do perform the natural log of this odd ratio, and we equate it to our y, that was alpha plus beta into x plus e. We can ignore this e, as I said earlier, for this derivation purpose. Okay, so we have this. Now, based on this alone, some people who are very good at math can say that since p is a probability, it must be between 0 and 1. But how do we people get this confidence that actually p is going to be from between 0 and 1? So let's do some arithmetics or algebra to get this confidence. So we took to remove this natural log, we just take exponential of the right hand side and the left hand side. So we get p upon 1 minus p and exponential of alpha plus beta x. and then just send this to the right side. Now what we get P as this expression. Based on this itself, we can say, because we know that exponential of anything can never be negative, it is always greater than zero. So we can, based on this itself, we can say that it is going to be a positive number divided by 1 plus that positive number. So it is not never going to exceed 1, since we are the denominator is always more than the numerator. But let's try to convert this into this logistic regression form. So to do that, we just divide the numerator and the denominator by exponential of alpha plus beta x. So when we do that, we'll get here. So this is much more closely resembling our sigmoid function, where z is alpha plus beta x. And if you have done any basics course of machine learning, you will see that actually this is what is represented as z, and then this probability is actually called as an activation sequence, and this function logistic regression is called as an activation function. Specifically in neural networks, but moreover in machine learning it is used, this kind of terminology. So this is how we are 100% sure that this p that we have given here using this order issue, the probability of occurrence, is going to stay within the range of 0 to 1. So we use this approach of logistic regression and train our model. So we'll have some inputs x, and we'll have their corresponding label, whether it is 0 or 1. So sometimes it will be orange or apple, can be used, it is used for classification. So in that case, we assign orange to 0 and apple to 1, and we train our model. We get the value of p. If it is greater than zero point 0.5, we give it as 1, and we perform a stochastic gradient descent or normal simple gradient descent or genetic algorithm anyway to get these alpha and beta to minimize the error between the difference between our predicted p and the actual y that we have gotten. So that we can, I think we'll learn in different coming weeks, that how do we do this and which kind of function we have to minimize. So we'll leave those things for the future. So just remember that this is how we prove that p is going to be between 0 and 1. Okay, so another thing was, uh, logistic regression is good for binary classification, but and it can also be used for this multi-class classification. But in that case, as I said, we have other classifiers that are much more efficient in doing the multi-class classification, such as the one we studied before this, that is linear discriminant analysis. It is far better in performing multi-class classification than logistic regression. Whereas if you are talking about binary classification, then you can use either of them. But when it comes to multi-class, it is advisable to use this linear discriminant analysis. Okay, so these were the few methods for classification. Now let's look at clustering. So as I said in the beginning of the session, that in clustering we don't use the label of the class of the observation, that y information of the classification, and that's why they are also called unsupervised, right? Okay, before we go to this clustering, we have KNN, which is also important. So let's discuss that. K nearest neighbor, which is a nonlinear classifier. Yeah, let's discuss KNN. The basic principle behind the classification methodology used by this KNN approach is it is going to look at its neighbors, K neighbors exactly, which you have specified, and based on those K neighbors, it is going to give the new observation any class. So, unlike logistic regression, there is no training required for KNN because it uses the information that is already given to it to make new predictions, and it is not a parametric classification, so we do not need to calibrate our parameters, which is what we basically do when we train a model. So using a figure, let's try to understand this. So in the more space, so let's say you have x1 and x2, a two feature classification where you have x1, x2, and y is the label. So you have some points, right? Some black points, and let's say some red points. Now I say that here is a point with no color. Now I want to know whether it belongs to the group of red points or the group of black points. So what we will do is we will calculate the distance of this point with all the existing points that I have given. Right? And after doing that, I am going to order or arrange these distances or these points based on their increasing distance. So let's say we have this red point here. So black point is the closest. This black point is the closest. And then there are two red points after that which are more close to it, and then we have another red and black again. So the list, if I just represent the color in the list or the class in the list, it will look like red, sorry, black, red, red, and black. So like this list will go on, and now you have given k as an argument, right, inside this classifier. What that k is, it is the number of neighbors that we have to consider. So I'm going to mute Debarma because okay, yeah. So we gave an argument k into this function that was the number of neighbors to consider while performing classification. So if I were to say that k is 3, then I'll go to this list. I'll take first 3 the minimum three distance points, and then I'll see which one is in majority. So if this here we see that red is in majority, so what I'm going to say is this new point that I had is a it belongs to the red class. And in the same way, we are going to do different analysis for other new points if I were to introduce you. So this method is very simple, doesn't need any kind of training and because it is not parametric and uses the existing data to make any further predictions. But at the same time, when anything is very simple, we know by now that people don't generally use that. That's why there are other methods that are preferred over the KNN. We'll see some example of KNN in our programming part of this session. Okay, so we have this. We have talked about some classification methods where we know the true value and the predicted value, and there are some accuracy calculation measures that were discussed in the class, which will tell you how your model has performed, how good or bad it is. So in that there was a Cohen's kappa coefficient, which was actually emphasized more other than the rather than the other coefficients. So we are going to see one example of this Cohen's kappa coefficient example problem. So let's first define what is our Cohen's kappa coefficient. So it gives us the measure of how our model performed compared to how it would have performed if it was just based on the probability, if it was just a random guess. So let's write that how our model performed compared to how it would have performed if it was by chance. This particular definition is not very clear, but let's see how we can compute it in real life. So you must be familiar with confusion matrix by now, that will have these entries of true positive, true negative. So let's say we have prediction here and model here. So we had here true positive. I'll just write it here so that we can write some values in this particular table. So true positive and then false. So this is positive, negative, positive, negative, false, negative. This is false, positive, and true, negative. So what I'm going to do now is I'm going to give you a scenario and I want you to tell me which values are going to go into each of these spaces in this table or a matrix. So let's say I performed experiments on total 70 people. I did a test on the 70 number of people. And we did a preliminary test, like we did a test based on our model and we did a very thorough actual medical test and we identified whether people were sick or not. So actual number of people who were sick in our test, one, actual number of people who were sick in our test were 35, and our model predicted only 25. So let me write it here as actual sick and predicted sick. Or maybe let's give this. Let me give you a simpler example. Yeah. So our model predicted 25 people to be sick when wait, when they were sick, when they were actually sick. But it predicted 15 more people to be sick when actually they were not sick. And this is so our model has told these people are sick. They are affected by some kind of problem when they are actually suffering that and when they are not suffering that. And our model told that 10 people were not sick when they were actually sick, and that 20 people were not sick when they were not suffering from any illness. So can you tell me now which of these value is going to go in which of these entries? So let's first see what is the true positive entry based on this data that I have given. So what is the true positive entry? If you recall what I told in the last session or last to last when we discussed about this confusion matrix first was true means that our model is said yes, and positive means both are aligning model and observation, and negative means model and observation are opposite. So why don't you take a gamble and tell me what will be the entry for true positive? So let me give you a hint here also that yes means that they are sick. Okay, so without wasting more time, let me just tell you that true positive means model predicted that they are sick when they were actually sick. So it is going to be 25. False negative means model predicted that they were not sick but actually they were sick. So it is going to be 20. Yeah. What about false positive? Means model told they were sick but they were not sick. So that is 15. And true negative model oh sorry, so this is 10, and model told they are not sick, and when they are not sick that is 20. So 20 goes here. So this is our confusion matrix based on the readings that we obtained. Now, what is the overall accuracy of our model? Overall accuracy is defined as the number of observations that were correct divided by total number of observations. So, if you want to calculate, you can calculate total or overall accuracy. It is going to be true positive plus true negative divided by false positive plus false negative plus true positive plus true negative. So we have 25 plus 40 divided by total that I gave already as 70. So this particular model is not performing very well because its overall accuracy is somewhere around 0.6428. Right, this is our P naught for the Cohen's kappa coefficient. So let's just write the formula for Cohen's kappa coefficient. It is P naught minus PE divided by 1 minus PE, where PE is the accuracy if the model was just based on chance. And how do we calculate that? We calculate that by adding the probability of this model being correct for yes, always yes, and no. So let me show you pictorially how we do that. It will be much more easier rather than explaining the theory, which is, as a matter of fact, actually difficult to understand. So when you made this confusion matrix, calculation of PE is very becomes very easy. So what you have to do is, for yes, or let's say positive, or for no, or let's say negative, what is the P probability? This can be written as PE1 and this can be written as PE2. So PE1 is nothing but total model. Oh, so I wrote prediction and model here. It should have been observation because prediction and model both are same thing. Okay. So total model positive divided by total number, that is n, into total actual positive divided by n. So let's calculate PE1. What is total model positive? Total model positive is prediction positive, that is 25 plus 15. So we have here 40 divided by 70 into total actual positive. What we have there is 25 plus 10, that is 35. 35 by 70. So what will it be? If you do the calculation, you will find that this number is 0.2857. PE2, that was probability for all no. So that is same as this we have written here. So let me remove this n because it might be confusing. By total observation. So we have total model negative divided by total observation into total actual negative divided by total observation. Okay, so what is total model negative? Total model negative is 10 plus 20, that is 30 by 70, and total actual negative, observation negative, is 15 plus 20, that is okay, that is again 35 by 70, and that is equal to 0.2142. So now you have your PE. 0 point approximately, let's say 0.5. So what will be the Cohen's kappa coefficient's value? It is P naught minus PE divided by 1 minus PE. 0.6, what was it? 0.6428, yeah, 0.6428 minus 0.5 upon 0.5. So you can do this calculation and write here what is the value of Cohen's kappa coefficient. Okay, so that was about the classification models. I wanted to discuss about this because uh, there might be an example problem or numerical based on this, not in your assignment, maybe in the answer. Okay, I've not gone through your assignments. If you have this problem in your assignment, then very good. Otherwise, you can now know how to calculate this for your answer if at all it comes. Okay, now let's talk about the clustering algorithm or clustering models, which are also called unsupervised because they don't need the label. What are some of the examples of this clustering algorithm? So two that we are going to discuss here, because we have already discussed about CART and SVM in last session. So the two that we are going to discuss now is K-mean and K-medoid. So what is K-mean? How does it work? Let's say you have set of data and you want to do some kind of classification. So what you do is you start by stating the number of clusters, that is K. That is the number of classes you want to divide this data into. Okay, sorry about that. Yeah. So in this particular case, you may be able to see that three classes. We can see that I have made here three classes. This, this, and this. But let's say we don't know that. So how do we go about doing this particular classification or clustering? Sorry. What we do is we assign randomly some points to class 1. Let's say we have chosen class K as 3. Some points to class 2, some points to class 3. Now, you calculate the mean of this group 1, group 2, and group 3 based on the points that you have assigned them. So, first step is to assign randomly the points to different classes. Second step, calculate their mean. Now, how many means we'll have? We'll have three means: mu 1, mu 2, mu 3. Third step, so we have to do this step for like all these points. Calculate the distance of observations with each mean. So let's say we did the random assignment, and our one mean came here, another mean came here, and third mean comes here. Now we are going to calculate the distance of each point. Let's consider one random point here with these three means, and the mean which is closest to this point, choose the class. So this also goes here only. Choose the class of mean closest to the point under consideration. So let me change this to some other color. This is blue, this is green, and let's take this, it's purple. So purple. Now you calculate the distance of this point from all these three means, and we see that the blue is the closest. So you assign this point as blue, and you do this for all the points, and you keep on doing this till no point, no further change is observed. And in the end, what you will observe is that your classification is successfully complete with blue. So we have purple, right? Purple and green. Now, all these problems of machine learning are actually subject to overfitting. So, if you give, in this particular case, we have three nicely distinguishable boundaries or the groups. If you can actually give k more than 3, and in that case it is going to try to find more and more difference between, let's say it is going to give this point, these set of points as red, right? So you can go k as high as the number of observations, and in that case every point will be its own class or group. That's not good. So to avoid that, there is a plot that we use to determine which is the optimal number of class. So we'll draw that particular plot. So it is called as an elbow rule. So you try to find the elbow which corresponds to the least error, and on the x-axis there is the number of classes. So you find out this point, because after that the decrease in error is very less, so it's not very efficient to go beyond that. And there are inbuilt functions in Python to find out this particular elbow. But rather than that, we'll plot it, and we'll ourselves will be able to identify that uh, as what is the good value for k. So there are some. So this is what is k-mean clustering algorithm. There are some disadvantages. One, I don't like stating all these advantages and disadvantages, but for this it is important to state that it depends on the initialization. The random initialization that we do of each points into a different class, that is an important or crucial step for this, because uh, it is said that you have to run this particular algorithm once or one or two times to get actually a correct classification. So it depends on initialization. That is something that we have to worry about. Okay, so I am audible, right? Gulshan, can you comment it if I am audible? There's not much disturbance. Hello? Okay, so I don't know whether I am audible or not. Let me check myself. 1 second. So,
So
yeah, I
yeah,
think I am audible. Okay, so let's continue. So this, because of this limitation and another limitation of stucking at local optima, we prefer another clustering algorithm, that is K-medoid. A weird name, but it performs better than the K nearest. Sorry, the K-mean clustering algorithm. The only difference between these two algorithms is that in the K-medoid clustering algorithm, we don't use mean. We don't use mean. Rather, we use a point. We use a point that has minimum distance from all the other points in the group. So this point is not fixed. This point will also change, because let's say previously our group was this. It was in the middle of the iteration. Let's say the red. Let's consider the red. The red group had these points. Okay, red group had these points. So the point in the, let's say this is the point in the middle, which is actually having the minimum distance out of all these things. And now what we do, we perform this iteration again, and we change up in the second iteration. The red group actually is not this, but select it, paste it, paste it here. So now in the second iteration, the red group is not actually this, but we make this black. Let's, yeah, now in the second iteration, somehow the red group actually changed it. Let's take this point to this. After two iteration or three iteration, let's say this happened. Then in this particular case, the center point, or the point which will be used instead of mean, will be this point, this point, because it is the point which is having the minimum distance from all the other points. So this makes this process, this K medoid algorithm, very computationally expensive, because every time you have to actually identify the point that is having the minimum distance from all the points in the group. Whereas in case of K mean, you just do the mean of these things and you get that. So this is about K medoid. Now what we should do? We have time, right? So we are going to do some programming exercises in to do this classification and clustering. So we are going to use LDA. Uh, we are going to do K medoid, and SVM. So last time I don't think I showed SVM example. So we'll do these things. So this is supervised. This is supervised. So we'll use one same example for these, and these two are unsupervised. So we will use another example for these. Okay, so give me a second to share my other screen. Okay, so it seems that the host only can share fine. So I have made a lab notebook. We'll use that. Please message if you are able to see the screen. Please put the message. Okay, so we are able to see the screen. Good. So first is LDA, linear discriminant analysis. So if you have not heard about this scikit-learn Python library, then I think you should go and take a look at it because it is the single best machine learning library that exists in Python, and we'll use also this library to perform all the things that we are going to discuss here. So first of all, we are going to import the data set. There's some wine data set is there. Each wine, how much alcohol and other contents it is having. Then we are going to use pandas because to make a table, and we are going to do some analysis in the table, and we are going to use NumPy for normal operations. We don't need NumPy actually, but in case we'll import NumPy and matplotlib.pyplot for plotting. So let's load the dataset. First we'll import all the packages. Then let's load the wine data, and let's store the observations in X and labels in Y. So we run this, and here is a look at the observation. So you have alcohol. These are the features, right? These are all the features, and we have these are all the samples in that. So if you just do x dot shape, you'll see that we have 178 samples and 13 features. Now just let's have a look at these features. We have alcohol as a feature, malic acid, ash, salinity of ash, and all those things as our features. And we have labels. Now we are going to do classification. So in this particular wine classification, we have three classes that you can get from y dot categories. So you have class 0, class 1, class 2. Now let's do this. Let's concatenate this y the classes. It's because this is a label data set, so we know what are all each samples class, which class they belong to. So we create a new data frame, that is a table, in which we will add the category, that is y, and let's see whether it is added or not. So we added the category y, and we named the feature. We kept it as a feature and named that feature as class. So it should be in the end of this. So you can see actually we have added the new feature, that is class 0, and there are class 1 and 2. So if you go for more than just 5 values here, let's say you go for 20 values, you'll see some example for class 1 or class 2. So maybe we need to go more. If you go till 100 values, yeah, you can see now there are some examples for class 1, and similarly there will be in the middle some examples for class 2. Let's keep it short to 5 examples for our visit. Now from this scikit-learn library, let's import the linear discriminant analysis. From scikit-learn sklearn.discriminant analysis, import linear discriminant analysis. This will import our model, and we are going to give our model we are going to assign a variable name to our model, that is LDA. And this is just, instead of doing all these operations of calculating the covariance matrix, you can do that as we have done in the last session, that uh, where we where we calculated all these we went through all the steps of the model, and then we saw that we can just use one line and use already existing code. So we'll do that for this session. So we have discriminant analysis model, we give it in a variable name, and then we use the fit function to fit the model. So this is xlda is the result of our model. So let's see, why did I use y.code? So if you see that in this we have class 0 and class 1, class 2, which are strings. So when we are doing any kind of mathematical operation, we cannot use strings. That's why we assign some numerical value to each of these classes. So for class 0 we have assigned 0, class 1 we have assigned 1, class 2 we have assigned 2. If you want to see check the length, you see that for 178 examples we have 178 coded classes. And what does it do? What does our linear discriminant analysis do? It gives us the linear discriminant, like principal axis, it gives us the linear discriminant axis. So we have, after doing this operation, we get two outputs, two axes for our linear discriminant analysis. So this you can access through XDA. Now, if you plot this with the class, you will see that this all multi-dimensional or multi-feature data has been transformed or translated into these two axes to classify, to increase the uh, distance between the mean and minimize the variance within each group. In the same as PCA, the explanation ratio, which actually stores the how much variability is explained by each of the axes, we can see that this one axis explains 0.687 and the other axis explains 0.3125. So we'll use these two axes, LD1 and LD2, and when we plot it to see how this has done, how good of a job it has done for classifying our data, we can see that it has in fact done a very good job, because here we can see the colors of these all scatter plots. We have given the colors based on the Y codes. That is 0 is red color, blue is the 1 is blue color, and 2 is this purple color. So you can see that we have done a successfully done the classification based on the linear discriminant analysis. Now, if you want to use this, the model is stored in this XLDA or LDA. So if you want to use this particular model for new data, so we can use this existing variable or model LDA, and we will get whether that particular data belongs to the red, blue or purple class, that is class 0, 1 or 2. I'll share this lab notebook as last time, so you can play around with it. So, but let's quickly finish the other uh, algorithms also. So yeah, so this was the linear discriminant analysis. Now, since we are fresh with the data that we have, Wine data, let's look at the support vector machine or support vector classification in the same way. So I want to so what support vector classification does? It identifies the line which has the minimum distance between the two classes, right? So here we have three classes. As you can see, we have done some classification here. And since I want to, and there are multiple features. So what linear discriminant analysis did, it transformed all those features into just two features, right? But this support vector machine, it preserves all those features. You can use that by not transforming the other features and have the classification in the three-dimensional space or four-dimensional space. But to avoid any, to have clarity and to represent it in a figure, I am only choosing two of the features. So that is the second feature and the 10th feature. So because in the Python the index starts from 0, so when I'm saying index 1, I'm choosing actually the second feature. So I'm using the x as these two features, and y target is our code, that is 0 and 1 and 2. And this is our model that we have that we use, svm dot support vector classification. The kernels that there is the linear kernel. So let's first see what linear kernel gives us. As you can imagine, instead of these curved lines, we are going to see straight lines. But let's see what it is going to give us. These are all just plotting functions that you can play around with in your own time. But this is something important, that we can use multiple features, but for the sake of clarity and representation, I am using this. So when you use linear, you will see that you get lines, right? Which is not a very good classification, if you ask me. So if you use poly, that's polynomial, then you can see easily how nicely these points are classified. There is some overlap. That is because I have not chosen all the features. We have chosen second one and 10th one. Let's say if we choose the first and second, so that will be 0 and 1. Let's see what kind of classification we get. So this the classification changed a little bit. And if we choose some other, let's say we don't want to use the first one, let's say we want to use the fifth one, the sixth one, sorry. And in that case, classification becomes even more weird. So the yellow belongs to the red, the blue belongs to the blue, which might not be visible, but when you run it in your own system, you'll be able to see. And then the brown belongs to the brown. So let me just change it back to some good value. Let's take the first and second, and a little better classification is there. So you can actually use all the features, but we will not be able to see represent it in this particular figure. So that's why I have chosen only two. Okay, now let's look at the clustering algorithms. So first we look at our k-mean. So we have already imported the plot function. Make make blob is nothing but which creates this data set for us, which creates this data set. So that's nothing to worry about. And k-mean is our main function. That is, you can see we have used sklearn for all these things. So we use our make block. So we get 200 data points, 200 observations, and then three classes, three centers, and standard deviation we can say, and random state 42. So what happens is, see, if I run this without this random state, every time I am going to get different set of data, but I want to compare the accuracy of my model when I change some parameters. So we seed the randomness. So when we say this random state 42, it means there is a fixed randomness, there is a fixed value that it is going to give to the feature. If I were to give 41, then there another value will come, but that will be fixed. If I don't change from this 41 to 42, that will be fixed. So we are going to use this 42. Let's just import them first and then use the random state 42. And you can see that we imported from the make blob function that is inbuilt in this scikit-learn the features and their true labels. So you can see that we have x1 and x2, two features, and 100, 200 number of samples. And you can also, let me just show you the true labels also. You can see the true label is also there. So we set three centers. So there is 0, 1, 2 true label we can see. Now standard scaler is going to scale our data, and we use that scaled feature data for our classification, because you see these values are big values like 9.7 and then 10, and in the below there might be some values which are much closer to, so we don't have that much. But what is advised is to make the value such that the mean is 0, is around the origin, and the standard deviation is about 1. That's what we do. We scale our data. So these are the scaled features. You can see all the values are small. So if you do the mean of this thing, you'll see that mean will be approximately close to 0, and standard deviation will be about 1. This is our scale data, and we'll use our scale data for the k-mean model. So here are some input parameters for the k-mean model. So initialization, this init describes the initialization, which is going to be random. Clusters 3. So this will be same. So you can have different. For now, just give 3. And we have maximum iterations. So what is this n init? It is the number of iterations that we are going to go for. So we are going to go for 10 iterations. Maximum iterations is 300, and random state 42. You can change it also. And this is the k-mean model. I have defined it and I have stored it in k-means. And we use this k-means, since we have used stored our model into k-means, we use the k-means dot fit function and use the scaled features to train our model, these scaled features that we obtain. So using these two lines, we can train our model. And these are all just some of the like how many iterations it has taken to get to converge, and how many what are the cluster centers. So what are the actual means, what are the means currently in of these three that is there, and then the inertia, which is not particularly important at the time, so I'll just remove that. So you can see that within two iterations it has converged. And we can I've used the same things here. So if you want to see the plot, this is how the plot looks like. Three classifications have been done. As I was talking about, how do we know that this is the best classification, this best number of classes that we should have given? So to do that, we have to go through a test called elbow test. What we do basically in that test, we change the number of clusters or the number of groups that we give to this k-mean algorithm or model. We change it from 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we see how the error. So the function gives us error, is the inertia, how the error changes. And as you can see, I have done from number of classes 2 to 11. For some reason the number of clusters 1 was not working, so we started from 2 to 11, and you can see clearly that the elbow lies at 3. So that's how we know that we have to give the number of clusters as 3. You can run it again and you can see that it's 3. Now we can also change here and see what happens if we give more number of clusters. Let's say I give number of clusters as 5. Let's say I give number of clusters as 5. Here is the main thing. I'm just changing the bookmark for this. And we trained our data. Let's see how the plot will change. So you see, there are new classes, new groups, 5 groups here. So this is the one: skin color, red or maroon, blue, purple, and sky blue. Some other color. So there are 5 different. And if you do more, let's say you give 20, so you will have 20 different classes. And we have a number of groups as 200, right? So let's try 200. Sorry, and cluster you have to do. So you see, every point is now a different group. But the best from the elbow test we know is the number of clusters. Now let's use the same scaled data that we have scaled here using the scaling function that is also inbuilt in the scikit-learn standard scaler, standard scaler, right? To perform the k-medoid clustering. So for k-medoid clustering, because it is not very common, even though it is better because it is so computationally expensive, it is not very commonly used. It is stored in a library called scikit-learn extra. So we download that scikit-learn extra cluster. We get the k-medoid model, and let's again use 3. And so if you remember in the PPT, it was said that k-medoid, the distance matrix, can be Euclidean and Manhattan, and there was one more that is not important. So we can change actually here the distance matrix from Euclidean to Manhattan, whereas in K-mean it is fixed for Euclidean. So and then number of clusters we can change here, and random state 42. So I don't want it to be different from the K-mean in terms of initialization. So we'll just give random state of 42, and then here we train the model, and this is just for plotting. So for 3 classes, we get a pretty similar plot. If you just look at this point here, you will see that this is the only difference, where this is purple and this is purple instead of red. Right? So that is only the difference. If you change it to Manhattan distance metric, then it will be further different. So if you see that now this point is fixed, but this point you can see is swapped. So probably this example is not the best to explain why this K midoid is better than K me, but I just wanted to show how to use these things in your example. So let's say if I instead of 3 I give 10, right, so it will give us 10, which I think will be different when we go for K mean. Let's see. This is for 10 and this is for 10. So pretty close. Yeah, pretty close. Oh no, so in this place we have some different classifications. So yeah, so you can see that k-medoid is giving different, and this is more accurate as the literature suggests compared to the k-mean. So that is so what we have done. We have discussed classification and clustering algorithms, and we have done some programming assignments or programming problems for the two, and we have discussed Cohen's coefficient, which is important for your exams. I have shown you, if you have the confusion matrix, you can easily calculate the Cohen's coefficient. And then we have discussed some programming about these clustering and classification models. I think that should be enough for you guys, and that should be enough for you guys to develop some kind of motivation. As I will share this lab notebook, Jupyter lab notebook, try to play around with the values of clustering and support vector classification. Try to change these features and see how this classification changes. Okay. So yeah, that's all for today's session. We'll meet on Sunday. Sorry, last time I had to postpone this session, but this Sunday we'll meet from 4 to 6. The usual time we'll have session, and we'll again try to do some more programming if it is possible in the next week content.